So, welcome to the virtual lecture on Group 17, which are known as, of course, the halogens. And so all of these are relatively important. We've seen already a lot of their chemistry in compounds of other elements. So we'll look at now the things that are basically unique to these elements or compounds containing them that we haven't seen before. And so all of these are diatomics. So there's a single bond between each of the elements, and this is how they're found in nature. You can have atomic versions of these, but you have to break the bond somehow. I also left off at the bottom astatine. There's not much of this in the Earth's crust at all. There's not much of it around because of its radioactivity, and so that also comes as a diatomic, but we're not even going to talk about that because it's so rare. And so if you look at these diatomics, right, what normally happens is the bond strength would go down as one descends the group, which means iodine would have the weakest bond and fluorine would have the strongest. And so the question is that the case or not? And the answer is actually no. So the fluorine-fluorine bond is 155 kilojoules per mole, which is weaker than the chlorine-chlorine bond, which is 240 kilojoules per mole. And so this is aberrant. Now the reason for that is fluorine, the atom itself, is very small. And so what leads to this bond being weaker is the fact that we have the bond here, but of course we also have lone pairs of electrons all around the fluorine. All right, so there's 6 lone electrons here, 6 lone electrons here. Because this bond is so short, because the atoms are so small, those electrons repel each other, and that leads to the weakening of the bond. So we can look at the elements now themselves. Fluorine is the most oxidizing element on the periodic table because what it really prefers to do is to gain an electron leading to cleavage of the bond to form fluoride. This is very favorable. And so fluorine will react with just about anything to give fluoride. Now remember from one of the previous lectures that oxygen actually brings out a higher oxidation state in an element than fluorine can, and that is because oxygen can form a pi bond when it reacts. And so that allows it to do that, whereas fluorine can't do that, even though it's more highly oxidizing. So there's only 3 elements that fluorine does not form compounds with. That's these 3. The 3 lightest noble gases. Now it turns out fluorine does react with the heavier noble gases. So those gases aren't so noble, which means they do actually make a few compounds, not a whole many, a lot of them though. And so some compounds of fluorine that are important. This is one. Now if I write it like this, with a subscript G, it's a gas. That's then called hydrogen fluoride. It's not hydrofluoric acid unless you put it in water, and more on that in a second. This stuff is very corrosive on its own, and it has an unusually high boiling point of around 20 degrees C. So it is a gas at room temperature, but just barely. And the reason for that, of course, is hydrogen bonding. The same reason why water has an abnormally high melting and boiling point. Same with ammonia, same here. So if we then take this stuff and bubble it through water, what we get is hydrofluoric acid. Now, all of the other hydrohalite acids, HCl, HBr, HI, are very strong acids and completely ionize in water. However, again, due to the hydrogen bonding situation present in this molecule, it is actually a weak acid. And so the proton transfer equilibrium that we can write is like so. Right? This will transfer a proton to water to give the hydronium cation, hence it's an acid. And the conjugate base is fluoride. Now, how strong or weak is it? It's still relatively strong. Its pKa is 3.2, but the pKa of HCl, for example, actually is a negative number. So what that means is a couple of different things. This is a weak acid. So in a solution of this stuff, you have all three components, undissociated HF, the hydronium cation, fluoride, anion. The other thing is, if you take a sample of sodium fluoride or something like that, NaF, and put that in water, F- does have basic properties, which means it'll take the proton off of hydronium, or off of water rather, and generate hydroxide. And so this is actually a base in aqueous solution if it's there by itself, sodium fluoride or something like that. The other acids, of course, being so strong, that's not the case. Chloride never gets reprotonated once it dissociates in hydrochloric acid. So one of the things that this is used for, and there's a number of them, is etching glass. And so if you look at, well, you can't right now, but if we were in a normal situation, if you look at the door going into the main office of the chemistry department, or somebody who has their name etched into their storefront window, that was done using hydrofluoric acid. It dissolves SiO2. And then you can rinse it away, and then you have the etched glass. The other thing, though, about this stuff is it's also really poisonous and dangerous to work with. Not that the other acids aren't, but this has the added difficulty of the fact that it can be absorbed through your skin, and then it goes and it reacts with the calcium in your bones and dissolves your bones. So if you're working with this as you would with any other acid, make sure you have proper personal protective equipment on when you're doing it. And so the other use for this guy is that it's a useful starting material for a whole array of fluorine-containing compounds, and we won't go into all of that. So moving down one, chlorine. This is also a gas at room temperature, but it has a very low boiling point, so it's much harder to condense. And one thing about this, we'll get to this in a bit, in terms of a way you could actually run into this unfortunate circumstance, is that chlorine gas is highly poisonous. And so it's generally known that exposure to only 30 parts per million of this gas, which is not a lot, for 30 minutes can result in fatality. So again, being around this is not such a good thing. Now this is prepared on a huge scale, 1 times 10 to the 8th tons per year, once again, because this is the starting material for all kinds of chlorine-containing compounds. Organic compounds that have chlorine in them, sodium chloride, if you're going to produce that, or things like this. And so that's why it's produced on such a large scale. Now, if we look at this material, again, it's a gas at room temperature. Hydrogen chloride is the gas form. If you put it in water, it is hydrochloric acid. This is very, very strong acid. It's completely dissociated in water, and again, the chlorine never gets reprotonated. So this is one of the stronger mineral acids out there. And of course, we'll use this for a whole bunch of different things. Now, one of the other acids containing chlorine that's pretty relevant right about now is conjugate base of it anyway, which you find right in here. There's a reason why this is named Clorox, and that is because it's a relatively dilute solution of this stuff, sodium hypochlorite. So a couple of things about it, right? This is a salt, and so the sodium is positively charged, and the ClO minus anion, which is the hypochlorite anion, is negatively charged. And so here, chlorine is actually in a formal +1 oxidation state. So all the halogens actually can do this. They can be in the -1 oxidation state as the halide, and they can have formal oxidation states of 1, 3, 5, and 7. And when you get up to 7, that's also kind of bad news, and we'll see about that in a bit as well. So right now, everybody's sanitizing everything, bleaching everything. A few things to note about this material, right? It stays good for quite a long time. So this is relatively concentrated, but it's still dilute by normal solution standards. And you notice it's also in a opaque bottle. That's because visible ambient light causes this material, specifically this part, the hypochlorite anion, to break down. And we'll see what happens there in a second. And so if you're storing bleach, you keep it in a dark bottle. If you dilute this further, so let's say a 1 to 5 solution, which is hopefully if you're using that for sanitation purposes is what you're using, then it becomes less stable, and really it's only good for 24 hours even if you keep it in a opaque container. So what are some things that you know about bleach? Well, of course, if I got on this shirt, I'd have spots all over it. It does take away dyes and things like that because it's a mild oxidant. And so the reason you might use bleach, for example, is if you're here in Oklahoma and you're wearing, let's say, a white shirt and you fall in the extremely red soil that we have here. If you've done that, those stains are kind of hard to get off, but bleach can do it. And the reason for that is those stains contain iron compounds. This stuff oxidizes them to something soluble, and they wash away. And so that's one use for it. It also kills germs and all kinds of things like that because it's toxic too. Microorganisms, obviously toxic to humans as well. So if you look at what's going on in that solution, though, it's relatively complicated. And so hypochlorite it doesn't matter what the cation is, this would be true for any salt of this stuff, is the conjugate base of a weak acid, hypochlorous acid. And so this has base properties. And this is the proton transfer equilibrium that occurs. So in your solution of bleach, you have not only sodium hypochlorite, but you also have potassium hydroxide, and you have HClO, which is hypochlorous acid. Now, it turns out that there's more than that going on. Okay, so I mentioned that this stuff degrades, and there's really no way to stop that even in an opaque bottle. So what will actually happen is this reaction. Now this is not an equilibrium. This is an actual reaction, meaning the equilibrium lies really, really far to the right. Once it happens, it doesn't go backwards to any large extent. This stuff can break down thermally or by interaction with light to chloride and oxygen. So this comes out of solution. Obviously, it's a gas and it escapes. Now, again, in a relatively concentrated, commercially available solution kept in a cool, dark place, this reaction doesn't happen to any large extent, but it does happen enough. So, in addition to this equilibrium right here, once you form this stuff, which you're going to do no matter what, the following reaction can take place. It can combine with that chloride that is generated from the decomposition of its conjugate base that I just showed you. And if that encounters an acid, which is also present. Now I'm cheating and writing as H+, that's actually there as hydronium, but it makes writing this easier. Actually, let's not do that. Let's do it right. All right, so this is generated by protonation of the hypochlorite anion, which happens. This is generated by the decomposition of the hypochlorite anion, which also happens. And this is an acid, and so there's hydronium present as well. When you have this stuff mixed with this, we generate that, Cl2. And so that is what you smell when you open up a bottle of bleach. It's chlorine. And there's not enough of it in there really to be toxic if you're, wiping down a surface or cleaning a bathtub or something like that. But, of course, you don't want to be exposed to that for long periods of time, and you don't want to be exposed to it in high concentrations. And so if you read on the back of that bottle, or any bottle of bleach that you buy, Clorox or not, what it will tell you is do not mix cleaners, period. Don't mix bleach with anything other than water. And the reason for that is if you mix this with something that's acidic, which some other cleaners are, some things contain vinegar, for example, right? That's acetic acid. You will generate, because of that first equilibrium, a lot more of this, which in turn means you're going to generate a lot more of that, right? Because according to Le Chatelier's principle, this equilibrium here is going to shift to the right, the product side, because this is a volatile gas, so it's constantly coming out of solution. And so that's why you wouldn't want to mix bleach with vinegar or something like that when you're cleaning. And so that's the reason why that warning is given. So we can look at these types of things as well, their formula and their structures. So why don't we take a look at those? And so all of the halogens do what I'm describing here. So you can replace chlorine with bromine, and the same type of deal happens. These are what are called oxo or hydroxo acids. And so what normally happens is once you start introducing more and more oxygen to the acid itself, the acid becomes stronger. So if we were to start, sorry, screensaver came on. if we were to start with the one we already had here, this, when aqueous, is actually a hydroxyl acid. So this is hypochlorous acid, and its Lewis structure is this. Whenever you have a hydrogen attached to an oxygen, which is attached to another element, like chlorine, that makes this acidic. So even though that looks like maybe, if you didn't realize that, looks like an OH group, you should think, okay, that's a base. It's not. This proton can dissociate and come off. And so this is a relatively weak acid, as we said, and that's that one. Now, when we quote-unquote add another oxygen, we generate this stuff. We're not actually doing this chemically, of course, but if you find this substance, this is chlorous acid. And it is a weak acid as well, but it's stronger than hypochlorous acid. And the reason for that is, you take a look at its structure. We're still going to have this going on. But in addition to the one oxygen, we see from our formula we have two. And so whenever you have that happen, the second or the third or the fourth oxygen is doubly bonded to the main group element in question. And so this exists for bromine and iodine as well. So when you do this and introduce a doubly bonded oxygen like that, that increases the acid strength. So to make a long story short, the more doubly bonded oxygens you have attached to the element, the stronger will be the acid. Now this one is still weak, but it is stronger than hypochlorous acid. So, moving on up the chain. Oh, wait, before I do that, sorry. What's the formal oxidation state of chlorine here? In this one, we said it was 1. In this one, it's 3. So you're becoming more formally positive, and you could probably imagine that an electronegative element doesn't like that so much. So the stability of these things actually decreases as you add more oxygens as well. This is a solid, in pure form, can be explosive. You can get it as a pentahydrate. So like so, HClO.5H2O, that is actually stable, especially if you keep it in a cooled refrigerator or something like that. This one gets much more reactive in terms of having its in its solid form. And so then, and yes, this is also, I forgot to mention, an oxo acid, not a hydroxyl acid. So are all the rest of them. So the next one is HClO3. We're talking about the acid, so put the aqueous there. The name of this one is chloric. Acid. And so if you look at the formal oxidation state of chlorine in here, it's 5. So not only is this an acid, it's a strong acid, and you'll see again the Lewis structure for this. It's also an oxidant. Now, the reason for that second attribute is that formal oxidation state of chlorine. It really does not like to have +5 oxidation state because it's an electronegative element, and so it will give up one or two of those oxygens in reactions as well as being an acid. And so if you look at the structure of this one, and we have our acidic proton, but now we have 2 oxygen atoms attached to the central element. And when you do that, the acid is strong. And so this completely dissociates in aqueous solution. And finally, last but not least, the maximum formal oxidation state you can have is the group oxidation state. So because chlorine has 7 valence electrons, this is as high as we can go, and we get this one. This is called perchloric acid. This is very strong. In fact, you can't accurately, there we go, measure its pKa. They're not even sure what it is, but it's some fairly negative number. It is also a strong oxidant because chlorine, again, is in the +7 oxidation state formally. And so this will react with just about anything. And so one of the problems with this is that it's very difficult to handle. In fact, you need to have a special fume hood, that's a perchloric acid fume hood, if you want to work with this stuff. And when you're done, what will happen is the fume hood will actually wash itself down with water to get rid of any of this stuff that got volatilized. This will react with wood, plastic, all kinds of stuff. And the problem is that if you have this anion, or the acid itself, it's explosive, shock sensitive, and this has happened actually once in an accident in our department in the UTL where somebody was using this stuff, and it wasn't a proper hood. Luckily, there wasn't much of it, and it detonated. So again, that's something you got to be really careful with when you're working with it. So the final thing we'll look at for this topic are the interhalogens. And polyhalides, specifically the polyiodides, because that's the most diverse one that there is. And so what are the possibilities of these compounds? You may be seeing a pattern here where we have formal oxidation state 1, 3, 5, 7. What's the X and a Y? X is a less electronegative halogen. And Y is the more electronegative one. So these are compounds of 2 different halogens. And they exist in these 4 possibilities where X is a less electronegative element and Y is a more electronegative element. So it turns out that for these 2 possibilities, all possible permutations exist. So what I mean by that, if you want specific examples, is we could have chlorine fluoride, ClF, where this is the Y and that's the X. Or you could have BrCl, etc. You could also have bromine trichloride. Or iodine tribromide, etc. So for these two possibilities, you can pick any halogen and attach a more electronegative element to it, either once or thrice. And so those are a fairly diverse group. If we go then to the next one over, these only exist if Y is fluorine. So there's only three possibilities as a result of that. Chlorine pentafluoride, bromine pentafluoride, and iodine pentafluoride. So in this case, the Y has to be fluorine. And for the final possibility, XY7, the only one that's known is IF7. There's only one possibility for that. And you notice what it's made up of. It's made up of the least electronegative halogen and the most electronegative halogen. This has actually a really weird structure that you don't run into too often. It's pentagonal bipyramidal. So you want to take a look at that structure. That's it. And so in the plane here, we have a pentagon consisting of 5 fluorine atoms, one on each apex, and 2 axial fluorines. That's just one of the few examples of this for 7 coordination that you can find. And so those are the polyhalides, the ones that exist. They're all reactive too. This is a good fluorinating agent. So is IF5. If you want to fluorinate something and you can't do it by any other way, that tends to be a good reason or a good way to do it. And then finally, the polyiodides. And so these are going to be negatively charged things with more than one iodine. So one of the things that's actually fairly interesting is that if you take I minus, so you take sodium iodide, for example, and dissolve this in water, and you add some solid iodine to it, that iodine will look like it disappears, and that's because what you're doing is forming I3 minus. And this is a classic thing that shows up on VSEPR structures and stuff like that. It's linear. Where the central iodine is charged because it has 6 valence electrons, 6 lone electrons rather, in 2 bonds, and the other ones are not charged. So that negative charge lies at the central atom, which will always be the case for these things. And so this is actually the most stripped down form you can get of the trigonal bipyramidal structure. And so that's the structure of that one. This stuff's actually pretty neat. You have to have a fairly large cation to stabilize it. And so you can if you want to have a salt of it, you could use ammonium, for example, as the cation. There's a rule of thumb that we've mentioned a few times in passing that large cations stabilize large anions, and here's an example of that. But this stuff is shock sensitive too, so what you can do is take a little pile of that, put it on the bench, and hit it with a hammer or something, strike it, and it'll make a fairly loud pop, and a little purple mushroom cloud of iodine vapor will come out of it. Provided you have the right, provided you have the correct cation, you can do this again. And so you can make I5 minus. And again, you need an even larger cation for this. And so the most common one, and there are others, is tetramethyl ammonium pentaiodide. So this big cation stabilizes this big anion. And if you look at what this looks like, it's V-shaped. So it's actually shaped like that. And again, the negative charge resides right there. Missing out the letters. There we go. A little unfair. And then finally, you can do this one more time, but you need an even larger cation. For example, tetraphenyl phosphonium iodide, heptaiodide that is, and that structure builds on the last one. Like so. This is really reactive and very hard to handle, actually. So you have to be gentle with it because it's shock sensitive as well. And the bigger cation is needed to stabilize that. And so those are the polyiodides that are out there. And finally, since we mentioned it, acetine, again, there's not much of it around. The reason for that is the most stable isotope is acetine-211. But its half-life is only 7.21 hours. So there's not much of that around. It is known that this has oxidation states of -1 and +5, but not much is known about it because it's decays so quickly. So with that, we will wrap up this lecture, and that's all we have for the halogens.